In this video, I'm going to introduce you to parametric equations, and we're going to start with a contextual scenario that will kind of give us an idea of the value of parametric equations, what they can do for us mathematically. So we've got a scenario here of two ships, the Andor and the Helsinki, and this grid that I've got graphed here is kind of representing the monitoring screen for someone who monitors ship traffic. And they're going to see both of these ships enter their screen and apparently look like they're on a course to collide with each other. And so what we're going to try to do is figure out, are they really going to collide? So let's start with the Andor. The Andor enters the monitoring screen 900 millimeters east of the origin, which I forgot to label, our little monitoring station there. So our Andor is going to enter the screen right here. I'll label that with an A. The Helsinki shows up on the screen 100 millimeters north of the origin. So here's the Helsinki ship. Now, after a minute, each of the ships has, of course, moved to a new position. The Andor's position is 3 millimeters west and 2 millimeters north of where it started. The Helsinki is 4 millimeters east and 1 millimeter north of where it started. And you may be thinking, okay, those numbers are really low because our units here on the grid, we're counting in hundreds. And yes, these are low, but we're going to assume that these ships are maintaining a constant linear path, and the movement is going to remain the same. And so even though after 1 minute, it's only 3 millimeters and 2 millimeters, we could say that after 100 minutes, it would be 300 millimeters west and 200 millimeters north. And so we can sketch a graph of the path of the Andor as well as the Helsinki. And so their paths would look something like this. We are just going for a sketch here, trying to be close to accurate, but it is just a sketch. So we can see that we've got linear paths here. They are definitely intersecting. We do have an intersection point. Will they collide is the question. So we're going to start by writing a linear equation for each of these ships. For the Andor, we can use the points. We have the point 900, 0, where it's starting, and we have a slope of -2/3, because our path there does have a negative slope. I'm getting the slope from our movement here where it's going up 2 and over 3. And so that would give me the equation y is equal to 0 minus 2/3 times x minus 900. Let's do the same thing for the Helsinki. We have the point 0, 100 where we're starting, a slope of 1/4, and so y is equal to 100 plus 1/4 times x minus 0. And the reason that we found those two equations is because if we're going to determine if these ships are going to collide, one of the things that we need to know is the coordinates of this point. Where is it that they intersect? And so I could find that intersection, of course, by setting these two equations equal to each other and solving and skipping over all of the algebra. You could use a calculator to find this intersection point. The x coordinate is going to be 545.45, and we could plug that back into either one of these equations and find the y coordinate of 236.36. So we have the coordinates of our intersection point here, but just knowing where the paths intersect doesn't really tell me whether or not those ships are going to collide. That is a question also that we cannot answer just with the use of these linear equations that we have written so far. And so what we need to do is to come up with a different way to express the movement of these two ships. The thing that's missing from our linear equations is the inclusion of time. We don't know how much time it's taking each ship to get to that intersection point. And so what I've done here is I've started a couple tables. I'm including time here at 0 minutes, 1 minute, 2 minutes, 3 minutes, 10 minutes, and then we're going to generalize with t minutes. They've done this for both ships. So with the Andor, we know that when it first entered the screen, it was at 900, 0. After 1 minute, it moved to the west 3. So now we're at 897, and it moved 2 millimeters to the north. So we went up 2. After 2 minutes, we would be at 894, 4. After 3 minutes, 891, 6. After 10 minutes, we would be at 870, 20. And so then the question here is, what is the pattern? For the X position, we're starting at 900, and every minute we're subtracting 3 units. So, and I didn't really leave myself room here to write that. 900 minus 3 times whatever the time is. For our Y position, we're starting at 0, and every minute we've just moved up 2 units. And so, whoops, didn't mean to switch colors yet. Sorry about that. So the Y movement would be 2t. And we can do the same thing for the Helsinki. And our table would look like this. So the information that we get here from the table, we could write this x of t is equal to 900 minus 3t, and y of t is equal to 2t. What I've done there is I've taken these two patterns dependent upon time and written them as two separate equations where x and y are both dependent variables depending on this new independent variable of time. So I've introduced a third parameter into the situation. And we'll do the same thing for the Helsinki. X of t is 4t, y of t is 100 plus t. These are both parametric equations. So now let's go back and consider our intersection point. So I have these sets of equations representing the movement of these two ships. We know that the paths intersect at this point, and our question is, when does each ship get to that point? Well, I can take the x equation for the Andor, this 900 minus 3t, and I can set that equal to 545.45. We can do the algebra there and solve, but I'm going to go ahead and tell you that t is going to be equal to 118 minutes. I could also do the same thing with the y equation. In fact, in this instance, it would have been a little bit simpler to solve. The 2t y equation is going to be equal to the y coordinate. We want to know when those two things are equal. T, again, is going to be 118 minutes. If this point is actually on the path that could be represented by these parametric equations, then time should come out to be the same for each of the equations being set equal to its corresponding coordinate. And so this tells me that it takes the Andor 118 minutes to reach that intersection point. Now, if we do the same thing for the Helsinki, 4t is going to be equal to that x coordinate of 545.45. We're going to get t equal to 136 minutes. Of course, we could do the same thing for the y equation and set it equal to the y coordinate. You're going to get the same answer. And so what this shows me here is that these two ships do not collide. They miss each other by about 18 minutes, which is not a lot, but certainly enough to prevent catastrophe out on the waves. So in this example, I hope you can see the value in being able to introduce time into equations that we would, normally just be able to graph in terms of x and y, but we are introducing the variable of time to provide a different level of meaning to the situations being modeled by the graphs. Now, one thing that I do want to show here is that our parametric equations are actually equal to the linear equations that we determined in the beginning. And this process is called eliminating the parameter. And what we want to do is eliminate this variable of t and end up with an equation that is only in terms of x and y. So I'm going to take the x equation and solve for t. And personally, I prefer to always start with the x equation. You can solve the y equation for t and then plug into x, but then you have to solve for y again. If we solve the x equation for t and plug it into the y equation, then we're already solved for y. So if x is equal to 4t, t is, of course, x divided by 4. And so I'm going to take that expression for t and plug it in right here, which means y would be equal to 100 plus x over 4. And if you look back at our equation that we wrote in the beginning, it is 100 plus 1/4 x, or x over 4. Those are equivalent equations. And so parametric equations, you can, if you begin with a parametric equation, we can eliminate that parameter of time and end up with an equation that we're used to that could be represented in a two-dimensional graph in terms of x and y. So now we're going to look at a couple examples of parametric equations. For each of these examples, we're going to make a table of values. We're going to sketch a graph, and then we're going to eliminate the parameter to come up with an equation in terms of x and y that could be represented by the graph that we have. So our first example, x of t is equal to t squared minus 2, and y of t is equal to t over 2. And we're going to limit the parameter t from -2 to 3. So the first thing I'm going to do is make a table. Here's my t value, and then x, and then y. I'm going to start at -2, -1, 0. I guess I need a bigger table. 1, 2, 3. If I plug in, I'll just work with the x equation first, t squared minus 2. So if t is -2, then I get 2. If t is -1, I get -1. If t is 0, that's -2. If t is 1, we get -1 again. If t is 2, 2. And then if t equals 3, we get 7. All right, I'm going to do the same thing for the y coordinate. And we get those points. So now we're going to sketch a graph. Looks like I need to go out to 7 on the x-axis. 4, 5, 6, 7. At least to -2 over here. And we don't need to go very high on the y. Okay, So I'm going to start with this point at 2, -1, right here. Then it goes to -1, -1/2, be about here. -2, 0, -1, +1/2, 2, 1, and 7, 3/2, maybe about there. And so if I connect those points, you can see we end up with kind of a sideways horizontal parabola. If you go back and look at our parametric equations, I think that should make a little bit of sense since we're squaring time in the x equation. One thing that we do need to do when we sketch parametric graphs is we need to always indicate the direction of movement. Because time is a factor, we are modeling change, we're modeling movement. And so in this graph, we started here at this point, and our movement goes in that direction. So we've got the table, we've got the graph. What I'm going to do now is eliminate the parameter. I'm going to start with x equals t squared minus 2. So t squared is equal to x plus 2, and t equals plus or minus the square root of x plus 2. And so if I plug these back into my equation for y, I'm going to get y is equal to the positive square root of x plus 2 over 2, or actually I should probably say and y is equal to the negative square root of x plus 2 over 2. And if you look at what we have graphed here, you can tell it's not a function. We are writing functions here. We're writing two pieces that would give us this graph. The positive piece here would give me the top part of the graph. The negative piece would give me the negative portion. And so that's one way to model this graph in terms of x and y. In this particular case, because we have ended up with a sideways parabola, I could have started with y equals t over 2 and solve this for t. T is equal to 2y. And then if I take 2y and plug it into my x equation, 2y squared minus 2, x is equal to 4y squared minus 2. What we have here is more of a conic representation of that sideways parabola, where x is a function of y. For our last example, let's consider these parametric equations. X is equal to 3 plus 2 cosine t. Y is equal to -1 plus 3 sine t. Again, I'm going to start by making a table of values. And we want t to be between 0 and 2 pi. And so I'm going to start at 0, and I'm just going to use the axis angles. Here, we're going to pick convenient values of t for our equations, which of course would be radian angles. And if I plug in 0 to my x equation, cosine of 0 is 1, times 2 plus 3 would be 5. If I plug in pi over 2, I get 0 here, and so this is 3. If I plug in pi, cosine of pi is -1, which would give me -2 plus 3 would be 1. If I plug in 3 pi over 2, we get 0 again, so that would give me 3. And then 2 pi, of course, is going to be coterminal with 0. We're going to be back to 5 where we started. For the y equation, if I plug in 0, sine of 0 is 0, so this is going to be -1. Sine of pi over 2 is 1, so that would be 3 plus -1, which is 2. If I plug in pi, sine of pi is 0, so I get -1 again. Sine of 3 pi over 2 is -1, so that would be -3 plus -1 is -4, and then 2 pi, course, I'm back around coterminal with 0, back to that -1. So let's sketch a graph of these points. Looks like I need to go out to 5, 2, 3, 4, 5. And I need to go up to 2 and down to -4. All right, so there's a good grid. I'm going to plot the points. 5, -1, 3, 2, 1, -1, 3, -4. And then, of course, we get back to 5, -1. Now, we have these points. We need to think about how to connect them. I'm not going to connect these with straight lines because we've got trig functions here. Hopefully, we would expect this to be more of a curve, circular, roundish type of graph, which it will be. What we end up with here is actually an ellipse. And we'll pretend that my graph looks a little more symmetric than it does. Again, we started here at 5, -1. I'm going to add direction arrows to indicate the direction of movement. But because we have used trig functions here in our parametric equations, we end up with a circular graph. Now, if you remember what equations of ellipses look like, I don't know about you, I prefer the parametric equation because it's much simpler to look at. But in fact, we're going to eliminate the parameter and see what this equation looks like as an equation of an ellipse. So I'm going to start with, let's write x equals 3 plus 2 cosine t, y equals -1 plus 3 sine t. To eliminate the parameter here, we're going to take a little bit of a different approach. I'm going to start here and I'm going to solve for cosine t. So cosine t is going to be equal to x minus 3 divided by 2. Over here, I'm going to solve for sine t, which is equal to y plus 1 divided by 3. And then instead of like using inverse trig functions, is what we would do to undo these to solve for t, but what we're actually going to do here is square everything. And you may think, why in the world are we going to do that? Just stick with me for a moment. I'm going to square everything. And then we're going to use our Pythagorean identity. We know that cosine t squared plus sine t squared is equal to 1. And so if I substitute, cosine t squared is equal to, whoops, I forgot my squared here. That should have been squared. Cosine of t squared is equal to x minus 3 squared over 4. I'm squaring that denominator to make it a 4, plus y plus 1 squared over 9 equals 1. And in this form, hopefully this looks familiar to you as the equation of an ellipse, whose center is at 3, -1. Let's look up here, 3, -1. There's the center. In the x direction, our ellipse should stretch out 2 in each direction. If you remember, this little distance is 2, and this distance is 2. And in the y direction, we should be going up and down 3 from the center, and that is indeed what is happening here on our graph of the ellipse.